Let us discuss now a single phase inverter with sinusoidal PWM. You have already studied the full bridge circuit while studying the DC-DC converter, the full bridge DC-DC converter. So let me draw the full bridge circuit. So this is one arm of the full bridge circuit. You have a top switch, semiconductor switch, bottom semiconductor switch. It could be either BJT or MOSFET. There is an internal body diode for the MOSFET, and for the BJT, if there is no internal body diode, you have to put externally this freewheeling diode. So you also put another arm just like this arm. So you have another BJT, set of BJT, top BJT and a bottom switch in this fashion. This is VCC, this is ground. So let us call this Q1, we'll call this Q2, this is Q3, this is Q4. And in between here we will have the load. So we will have an RL load, let us say L and R. So this is our full bridge converter. This full bridge converter, depending upon the way you modulate it, it could provide DC-DC converter if you put a transformer with center tap secondary, or in this case you are putting LR, the voltage across the centers or center points of the bridge will be AC voltage. Now we want to get a special quality of the AC voltage. We want to get the AC voltage which is having a fundamental of a sinusoidal, 50 Hz sinusoidal, so that when you filter it out, you get back your fundamental sinusoidal PWM. So you get your sinusoidal wave shape. So we need to modulate the switching pattern of the switches in such a way that when you filter out the voltage waveform which is occurring here, you will get the fundamental sinusoidal wave shape. So let us see how we go about doing this. Now the switches Q1 and Q2 should be mutually exclusive. When Q1 is on, Q2 is off, so that there is no direct shoot through current. And when Q2 is on, Q1 should be off. Likewise, Q3 and Q4 should be mutually exclusive. Q3 is on, Q4 is off. Q4 is on, Q3 should be off. Now, therefore, we can say that if this is A and B, and if you are giving a PWM here, what you give here is through a NOT gate. So it will be the inverted signal. Likewise, so we call that one as PWM A. Likewise, on this side also, you have to give to Q4 the inverted signal. So you can say this is PWM B. So now how do we get this PWM A and PWM B, and how do we get the sinusoidal PWM pattern across the center arms of the bridge voltage VAB? So let us have a look at that. So now let us draw some waveforms and try to understand how sinusoidal PWM can be established. So let us take a time waveform and let me draw the modulating signal. This is supposed to be the sine wave modulating signal, and it could be a 50 Hz sine wave if it is for a 50 Hz application. Now across AB, after filtering, we would like to have a sine wave shape like that. So let us compare this sine wave with a carrier. So the carrier is a triangular carrier which is between these two limits. So let us draw that carrier waveform. So the triangular carrier is in this fashion. It is between these two limits, and let's say these limits, This is the triangular carrier, and it is between the limits of -1 to +1. This is 0. So in general, you choose a carrier waveform frequency which is greater than 20 times the frequency of this fundamental modulating signal. So keep that in mind when you are choosing the carrier frequency. So the carrier frequency, if you choose 1 kilohertz, at least 1 kilohertz for a 50 hertz waveform, then it is exactly 20 times. So anything greater than 1 kilohertz is a good choice. So but normally the frequency of switching of these switches are much higher. So it will be, carrier frequency will be of the order of 20 kilohertz or 50 kilohertz, and the fundamental frequency is the order of 50 hertz. So there is a sufficient ratio, much greater than 20. So next, let us plot the waveform that you get, PWM A. So we will plot PWM A. So these are the intersection points, critical points, where the modulating signal is intersecting with the carrier signal. So let us mark that points and pull that down in this fashion. So the PWM A is generated in this fashion. So you have a comparator plus, minus. So you are having the modulating signal sine wave given to the plus, carrier given to the minus, and the output of that is the PWM signal. So which means that whenever the modulating signal is higher than the carrier, you will get a high, and whenever the modulating signal is lower than the carrier, you will get a low. So let us draw that. So we get a low here, then it goes high because modulating signal is higher than the carrier. Then in this time period, you see that the modulating signal is lower than the carrier. Let us mark that. Here the modulating signal is higher than the carrier. So on, you can draw the waveform PWM A in this fashion using this logic here. Now here, this at the bottom Q2 switch, we have, let us say, PWM A bar. So we can plot PWM A bar, which is, let me drag down these critical timelines and invert PWM A to obtain the PWM A bar in this fashion. So this is PWM A bar. So we have the switching pattern for the arm 1, the A arm, Q1 and Q2, given in these two fashion. Likewise, we should generate Q3 and Q4 also. Now for that, don't use the same modulating signal. See, if you are giving a modulating signal to the A like this, then for B, you give the modulating signal which is 180 degrees phase shifted, so that when this is positive peak high, this will be negative peak high. So there will be voltage difference across A and B. So you do the following to generate PWM B and PWM B bar. So PWM B. So let us give a 180 degrees modulating signal. The same modulating signal, 180 degrees, pass it through a 180 degree inverter, and use that compared with the same triangle. Don't change the triangle, with the same triangle, and draw the PWM waveforms. So let me mark the critical time points. There is a critical time point here with the red waveform, the 180 degrees phase shifted waveform. There is another critical point here, so on. You mark the points of intersections. Now after having marked the points of intersections, use the same logic as here. Whenever the modulating signal is higher than the carrier, you have a high. at PWM-B. And whenever the modulating signal is lower than the carrier, you have a low. So we have a high here, a low, high here, a low, high and low in this fashion. You see PWM-B. Compare PWM-A and PWM-B. PWM-A, you have more pulses, more wider pulses during the time when this is positive. Likewise, PWM-B has more wider pulses when the 180 degrees phase shifted is more positive. So, PWM-B in a like manner can be obtained by basic inversion. So, let us invert PWM-B to obtain PWM-B bar. So, this is simple. So, now you have PWM-B and PWM-B bar. So, all the switches Q1, Q2, Q3, Q4 have the pulses in this fashion. Now, let us plot VAB. Let us plot VAB, and across that should be the pulse width modulated waveform. It should be the sinusoidal pulse width modulated waveform, because it should contain within it the fundamental sinusoid, that is this fundamental sinusoid, which we should be able to extract by filtering. So how does that wave shape look like? So if you look at the waveform, if you look at the potential at A, it is, if Q1 is on, this is VCC connected here. If Q2 is on, A is connected to ground. So this potential VA with respect to ground swings VCC to 0, so which will be something like the PWM waveform itself, but only the amplitude will be VCC. Likewise, potential at B with respect to ground will swing from VCC to 0. It will be like PWM-B, only the amplitude will be VCC. So the difference between PWM-A scaled with VCC and PWM-B scaled with VCC, the difference between those two waveforms should give you the voltage waveform VAB. So let us draw that VAB, and let me draw down all the critical points so that it will be easy for us to draw the waveform. So now take this first part, PWM-A, PWM-B. So PWM-A, the A part and the potential at B, they are similar. This is also at VCC. At VCC, they will cancel and you will have a 0 here. And then here PWM-A is having a pulse, PWM-B is not having a pulse, so you will have a positive pulse in this fashion, where this is VCC going up to an amplitude of VCC. Then PWM-B is 0, PWM-A is 0, VAB is also 0. PWM-A is having a positive pulse, PWM-B is 0, so therefore AB will be having a positive. Now here you have PWM-A is a positive pulse, PWM-B is also having a positive pulse, so it will be 0 at the output VAB. And here PWM-A is having a positive pulse, PWM-B is 0, you have a positive VAB, and both are 0. PWM-A and B are 0 at that point, so here it will be 0. Again PWM-A goes high, PWM-B being 0. Here PWM-A and PWM-B are same, cancel and become 0. And here you have PWM-A, both are 0 here. And at this point you have PWM-B, which is positive, PWM-A is 0, so it goes negative here. And you have PWM-A and PWM-B coming in together, so 0. PWM-B is positive, PWM-A is 0, so you have negative, VAB is negative, and 0. Here again it is negative, 0, because these two cancel, negative, 0, so on. So in this fashion you get VAB, which is having pulse width modulation, and this is a pulse width modulated waveform. The widths are varying according to the sine pattern, and this will have within it the fundamental sinusoid which was used for modulating the carrier. So when you filter it, you will get the sinusoidal wave shape out of that, filtering out the high frequency carrier. In the generation of the PWM signals for the various semiconductor switches Q1, Q2, Q3, Q4, there is a practical problem, and to solve that problem, there is a dead time that we need to generate called the dead time generation. If you look at these waveforms here, you take PWM A and PWM A bar, or PWM B and PWM B bar. They are mutually exclusive, 180 degrees out of phase. So when Q1 is on, Q2 is off, Q2 is on, Q1 is off. Look at these two waveforms. They definitely are inverted, 180 degrees out of phase. However, the problem occurs at the transition. Look at this transition, which is indicated as an instantaneous transition, and at the instant when Q1 is going off, Q2 is going on at the same instant. However, in practice, in reality, things don't happen. The switching on and off doesn't happen instantaneously. There is a finite time. So in a finite time, you will see that Q1 is going from the on state to the off state, and in a finite time, Q2 will be going from the off state to the on state, and in between they will be in the active region for some period of time when both will be conducting. During that time, there will be a shoot through directly from VCC Q1, Q2 to the ground. So that is called the shoot through current. This is not desirable, because that will cause Q1 and Q2 to deteriorate, or you may have to overrate the devices, which is not actually a good thing to do, because it can be very costly. So in order not to have these shoot through current stresses, we provide dead time. That is, we turn on this a bit earlier, and we turn off this a bit earlier, and we turn on Q2 a bit later, so that you can fix a period for a period of time called the dead time period, when both Q1 and Q2 are off, that you have ensured Q1 is off and Q2 is still not started on. So this is a problem that we need to solve. So we are solving this by this dead time generation, and let me explain to you that. Let me take just only PWM A and PWM B, but it is valid for PWM B and PWM B bar. So the PWM A and PWM A bar, how do they look like? Let me just draw for one switching period. PWM A bar is inverted in this fashion, like this. So this is the problem, this point of switch over transition. PWM A is falling low, PWM A bar is going high, and also during these times. And what is it that we expect? Let me make some space here. So what is the new PWM A and PWM A bar that it should look like? So let me create a dead band zone. Let me create a dead band zone, and during this zone, both PWM A and PWM A bar should be low, which means both the associated switches Q1 and Q2 should be off. So which means that PWM A should go low earlier and come up later in this fashion. Going down should be earlier. Say likewise, PWM A bar should go up later and come down earlier in this fashion. So in this fashion, you have a dead band here, and that is called the dead time. And this can be a fixed time, and it is normally very, very small percentage of the on times, and this is the order of 1 to 2 microseconds. So how do we implement that? So normally if you take the PWM generation scheme, you have VM, that is the modulating signal, which is the low frequency sine wave, VC, which is the carrier signal, is the high frequency triangular carrier, compared in this fashion plus and minus, and you get the PWM output. And that PWMA is inverted, and you will get PWMA bar. So this is the normal way of generating as we discussed. But let us now generate with which will give you this dead time generation inherently. So let us first have this carrier. Now this carrier, this is now translated. So let me have this V epsilon, a very small DC voltage V epsilon, which is added and subtracted to this carrier. So this carrier plus and minus here. So if you see, this is VC plus, which is a small epsilon DC bias is added to the carrier here, and to this VM is now compared with VC plus, and that will generate PWMA. And in another case, you have V epsilon subtracted from the carrier, which means it is brought down a bit, level translated towards the negative side, average, and that is called VC minus, and that is actually added, that is plus sign, and VM is minus, subtracted, and you will get the PWMA bar. So this is the scheme that we will use for generating PWMA and PWMA bar, and if it is for the other phase, PWMB and PWMB bar, similar such thing. Let us just have a look at the wave shapes to understand this a bit. So let me have between these two limits what is supposed to be the actual carrier. But this is not the carrier that we will use. We will add a small epsilon to this carrier and get VC plus and VC minus. So when you add a small epsilon, VC plus will look like this. It is shifted up by a small epsilon. So it is going to give me, the epsilon is converted as a time shift here. And if I subtract it, V epsilon is subtracted from VC, you will get VC minus. So it is in this fashion. It is now slightly lower. So you use VC plus and VC minus for comparison. VC minus and VC plus is used for comparison. So with VC plus, we are doing the regular comparison of the modulating signal to the plus terminal of the comparator. VC plus is given to the minus terminal, and PWMA is obtained. So let us get that. So this is the modulating signal. Now let me draw the crucial points here. These are the crucial points where the modulating signal is intersecting with VC plus waveform, the green. Modulating signal intersecting with VC plus, modulating signal intersecting with VC plus, so on. Now let us draw the PWMA waveform. PWMA. What is PWMA? Whenever the modulating signal is greater than VC plus, it will be a high. So here it is greater than VC plus, high. Here VC plus is higher, you get a low at PWMA. Then high here at this point. So in this fashion, you get the PWMA waveform. What is PWMA bar waveform? VC plus is given to the plus terminals and the modulating signal the minus terminal. So whenever VC minus is greater than VM, you get a high. So whenever VC minus, now let me draw the waveform for PWMA bar, and let me mark the critical points of intersection of VM with VC minus, that is a red triangle. So whenever VC minus is higher than VM, it is having positive like this. So you see that you have this dead band, a fixed dead band as determined by V epsilon. So V epsilon will will determine what is this fixed dead band. Irrespective of the pulse width, this fixed dead band will be given between PWM A and PWM minus. So this is the dead band that will be used to protect or avoid any shoot through currents in the arms of the full bridge circuit. So in this way, you can implement a sinusoidal PWM with deadband generation or a dead time generation to obtain single phase sinusoidal pulse width modulated inverter.